load is in electricity for each season, right? There's 2 seasons, don't do every month. So unfortunately, again, this is a bit strange for you because it's for southern hemisphere, and then you need to think if winter is a different period of the year. That's a little bit tricky. But for us, it's obvious that June is winter, but maybe for you it will be a little bit strange. But anyway, try to think about maybe you're gonna come to Australia and work there. Obviously, if it was here, it would be slightly different, right? So it's very, very location dependent, this START analysis. So anyway, you come up with your energy demand for each month, okay? But you can see those values are always between 20 and 30 kilowatt hour, a little bit more than 30. For instance, in Singapore, you would use a lot of air conditioning. It's actually Singapore, the electricity demand would be quite high. Because you don't have heating, but the air conditioning is kind of expensive. Yeah, electricity bill must be high. So Australia, no, because particularly Melbourne, actually the cost is mostly winter because of the cold. And then particularly if you're outside city, then the temperature tends to be quite low. Therefore, typically for Melbourne, the temperature, the auditing, for other area of Australia like Queensland, no, the air conditioning becomes more relevant, not as bad as Singapore, I think. The temperature is much lower, not that humid either. So anyway, depending on your location, try to figure out what are those values to put in here, okay? And yeah, it would be a bit difficult for you because you don't know the place, but I linked you with a lot of material that you can have a look at and do your findings about the climate zone that they are looking for. Obviously, so Australia will be a different zone, like Queensland, Western Australia, South Australia, and the south, the area of Melbourne. The climate is slightly different, right? So Queensland tends to be sunny, very sunny, very high. If you are lucky, you get a Queensland location. Your project is beautiful. Yeah. If you get in Tasmania, they probably want to change the type renewable energy. Say sorry, I want a wind or hydro, probably better, right? No sun, not much sun. Melbourne also is not great for sun because when there is, it's good. But it's very unstable, so you can have, because actually it becomes, because of the sky is very variable, there are a lot of clouds, they come and go. And so you might have a very hot moment and then all covered, so when it's covered, it's not good. So anyway, you can look at those information there.
Our own house. Details, right?
You can also use your own that you have at home, really. Your own bill, except that for Singapore, your bill would be very dominated by the air conditioning. I have no idea what is the load here. Because houses will be smaller, so less to cool. It's good, because if you have something big, it would be expensive. I have no idea the cost of electricity in Singapore either. Interesting study. I think I'm gonna write a paper on this. But yeah, so you can use as an example your appliance. That's right. It's just to get used to this kind of analysis. Then what happens once you have this table here? You create this table here. You can import that in SAM. Okay. Okay. Now let's move back to SAM. All right, so this part in SAM is electric load, okay? And this, you see it's in here, right? And so you just look for monthly value. So here, monthly value, any value, you see you can put them here. Just copy and paste. If you have an Excel, just copy inside there and that's it. Okay, so January is the total of the month of January and kilowatt hour that you need. So 701, whatever you're getting is the number you're getting here. Okay. Then you can scale electric load to profile. Tick that box here. What does it mean here? This means that we have an electric load profile. Okay. So one thing is say I need 700 or 800 kilowatt hour in a month, but how much I'm actually consuming every hour? Think about it. It's quite different problem, right? What is the load profile? In fact, the load profile that I gave you as an example, I took a load profile of a house in Sydney. Right? So I didn't have a load profile for each location, so we just used that one. But really, this is also very much dependent on the load profile that your house has, and this depends a lot on the location, of the habits of the people in the location. For instance, during COVID, people were staying off, so the load profile was totally different, right? Now we're going back to the norm. But what happens typically, you have a load profile. Let's see if there's any more details here. No, we can look in SAM. So what you're doing here, you first of all you can load import. Okay, it's already imported in mine. You know, if you had to do, you would import exactly the file that I put in there, which is a text file called bank style. That's it. Yeah. But you also don't need that because you can create your own profile by you see. Calculate load the data. Here, you see here you can calculate your load profile by the house that you're having. Okay, and it's I mean I just decided to input that one because it's simple. And then you can view load data, which is this. Okay, and you can see, for instance, you can zoom. This is you zoom in here. Let me see. I think maybe you can do. Sorry, profile. So this gives you a view of the profile. Typical profile during January, typical day. So what is showing here that during the day when you are actually using the load, okay, which depends a little bit of the month from this profile. So basically you have a peak at this point here. That's when you maximum use the electricity. Anyway, so this is just the when you are actually consuming this electricity. It's not just the total. So it's scaling to your monthly value, but use that profile. Anyway, that's all. So there's not much to do here. It's only to input your monthly value. Okay, what next? So then, okay, we need to choose the module. And here we are. So we go back to module. Here you have a lot of modules, so you can choose whatever you want, really. But each module, you will have the information about the nominal efficiency, the maximum power, all the things that we have studied, okay? So you can, for instance, look for a module that has a high efficiency, which would be monocrystalline silicon. This one, for instance, I choose is a multicrystalline silicon. And then you can see also what is the temperature coefficient. So all this stuff we just use in manual calculation, right? So and exactly what. So I just put some information in your report about what kind of module you are using. Also, it's a good idea to use something not too small, like I mean this 300, like. Not use something. I think they're all pretty big. This module, it's in between even up bigger, right? So anyway, you can see what you like. It there quite a lot. You choose one of them, right? So it's not really important which, but you can inform in the report. Then there is the inverter. So this is the most difficult part, to choose the inverter. How do we choose the inverter? Alright, so let's look at, so in your report, Lisa, you will talk about this. So here is just, what I got? Okay, so these are just settings to do, but if you use the file I give you, this setting already there. It's hard to read here. Nominal, okay, so he needs to know how to do the temperature correction, so we do with the nominal operating, so the derated temperature method with the nominal operating relative temperature. You can do also with using heat transfer, right? It's just two different methods. It has embedded the calculation to either one or the other. And then mounting, it's mounted, etc. But if you use mine, you just leave as I did. If not, just make sure if you start from scratch, you need to set those things, right? Otherwise, this calculation a little bit different. Because I didn't explain the heat transfer, so I just don't know what it does, right? So we know what it does with the nominal operating temperature, that's all. And just because it's familiar. Now, let's go to the what is the size? So, to size roughly the inverter, what we need to do is to look at what is my design month, right? So, I decided to look at June. So, in June, I saw that I have 24 kilowatt per day of energy demand, and I have 2.8 peaks an hour, right, from that graph in June. Then I assume that I have a 0.75 total derivative factor, and I calculate how many modules I need roughly. I know what is my module power because I've just chosen. So in my case was 325, you would choose something else. I have my peaks an hour, total derivative factor here, daily, and roughly I calculate that I need probably 42 modules, right? Roughly 14 kilowatt. Okay. Then what means that I need to look for inverter roughly that power. So your inverter is roughly the power of your PV system, power-wise. It can be slightly lower. Okay, it can be slightly lower. Why? Can you tell me why it can be slightly lower than the system power? Think about that. Because the inverter, what it does, inverter convert the power, which is DC, in AC, right? Because your appliance, they work with the alternating current, where the photovoltaics produce direct current. So obviously the power needs to be close. But why the inverter can be smaller? Because first of all, why we want this inverter smaller? Why we want? Because it costs less, right? Think about money, right? You pay for what is the power of the photovoltaics and the inverter. So if the inverter is too big, for instance, more than 10 kilowatt, that goes into a different set of cost than something below 10 kilowatt. Okay. Then okay, want to spend less. Then can I make it smaller? Yes, because the maximum power of your PV will never be reached. Because it is achieved at temperature which is never happening under the sun, particularly under peak sun. So you will work always slightly low. So you can afford to have an inverter that handle just a little bit lower power. How lower? You can go even 30% lower. Not more than that, because then you start cutting. So it doesn't invert, you're not able to work. When the power goes up, you can't convert it, okay? All right, so therefore you can look for an inverter which has roughly, so I was thinking about 14 kilowatt. I look for an inverter of 12 kilowatt here, okay? It's still big because my system is gonna be big. Marble is not very good, and so it's quite big inverter. And let's see. Once I choose inverter, then I need to look at what are the properties of this inverter. So the DC nominal voltage, okay, is 370 volt DC. And then I need to look where it's operating, which voltage is operating, between 480 and 300 VDC. So that's what I need to set up my series and parallel for the photovoltaics. And then I simply give you some guidance here on how to size it. And again here I provide you an Excel file to do that. It's called, oh sorry, I'm going a bit slow, okay. Excel file is called, backs down, okay, it's all in order, okay. It's called PV number of module sizing, something like this. So this one is you can use just to have an idea of what type of system you're gonna make it. Okay, so let's open that file. It's here. So here you will set the VCC, which I mean this is the it's a voltage that you assume is gonna be the voltage you controlling the battery. Because you have also a battery, don't forget about that, right? So when you have a battery, the inverter also has a charge controller to avoid that the battery is overcharged. So let's say that we set 420 because this is a value that is good. It's kind of midpoint between 300 and 480, which is the maximum range of operation your inverter. And also, actually, this is a maximum power point controller as well. So I put it to 420 here. Then you can assume that you have your PV on the roof and the inverter might not, it's not on the roof, it's not generally. So you have some cables, so you have some losses, which can be 0.93% losses, okay. It's default, you can use it as a default value. So then this is the voltage at the PV system. This in blue is calculated from the above. And here you put the maximum voltage of your the module, okay? Remember this, you can read from the module system here. And then go module. Here you have maximum power voltage and maximum power current, okay? So these are the values you need to put inside Excel. So maximum module maximum voltage, and so here it calculates how many in series, obviously. So the series will be the voltage of the PV system divided the maximum voltage of one module, right? So here I found out is 10.3, so it means I can put 10 modules in series. Okay. Then here you put the VDC of your inverter, nominal VDC of your inverter, energy daily that you just calculated before. Backup days, okay, here, because we have a battery, right? So what's for, okay? So a battery, if you have grid connected, really, maximum is 1 day of storage, yeah? Generally, the battery is used only for storing some electricity when you overproduced, and you can send to the grid and store in the battery. And use when the peak demand so that you save energy from the grid. So it doesn't have to be a lot. So here I choose 0.3. You can store a little bit more than that. That's 30% of the time, or during 24 hours. So it's about 7 hours of storage. But you can increase it, up to 1 day. Obviously, if you go up, it becomes really big, and so I put 0.3. Here you put the inverter efficiency. Again, it's something you can read on the data sheet of the inverter. I think mine was 0.3. Depth of discharge. This is very important. This is for the battery. Okay. So if you have a good battery, you can afford the depth of discharge much higher, like maybe even up to it's maximum 80%. You can afford 60% for lithium-ion battery. If you have a cheap battery like lead-acid battery, then you wanna because they will die, before the 20 years, and they will be unusable after 10 years. But yeah, you can push them up to 0.4 as a depth of discharge, because clearly, if you keep this low, then the system will be bigger as well. So anyway, and here it calculates for you the battery size in ampere hour that you need for the system. Here you have the efficiency of the battery, and this stuff that calculates. This one, a peak sun hour design month. You have to input this. Sorry, this should be in green. You need to input. It should be in green. This one, because it's an input value. Okay, so I use green for input and blue is calculated. Then this calculate the current and the photovoltaics. This is the module maximum current. Also, you need to input. Fuse rating. Okay, so here maybe you don't find this information. It can be 20 or 15 ampere. 20 can be used as a default. It depends on the standard. For in Australia, it's 520 ampere. And here it tells you how many strings. Strings are you put the module in series, like in this case 10. Each of these series is one string. Okay. So here we say that we have 2 strings. Always, if you can, always round it down. Okay. And this is in parallel. I round it out because if I round it down, I can also round down, but then my system may become a bit too small, 20 modules, but I want around 40. So I got 2. And then so basically I have 40 modules in total. So at the end your size has to be done based on electrical parameters, not just the energy balance is good, but then we have to cut those cables, right? It makes sense. It doesn't explode. So roughly we need to have those that. And so therefore at the end here you have about 40 modules, and it calculates your final power. Yeah, I just put some losses, so you can use it the same as the default. Okay. So what you need to change are probably this value where you want to control your charge, the voltage you want to control, and your module maximum voltage as well will be different module by module. The VDC, this will be different. So the depth discharge may be slightly different. There are a few things you can change in your project, okay, compared to mine. And then, okay, so in my case here, you see that the string is, what is called string is this. Sure, okay. So the string should be. It's strange because here it seems to. So this is this one string, so you have two strings in parallel, and then these two are, this is a fuse here, right, a 20 ampere to limit current, and then another group of two strings in parallel, so for a total of 40 modules. Okay, and the voltage you have here and current is calculated by that little Excel file. This is just to give you an idea how to do the sizing. At this point, then you're fine, right? When you are sorted here, you're pretty much done. There's not much else to do. Then you basically go. You have inverted decided design, system design, and here where you have two inputs, you see modules per string. I said 10, two in parallel, and I have two subarray for a total. So you have to set down this here for 40 modules. So your work will be different, right? So I don't know. Yeah, so this one has to be set slightly different. So you can have more, or you can have less. Organized in different way. You can put more in series, more strings in parallel. Yeah, so it depends on your parameters, electric parameter. And here you can see I'm getting a DC to AC ratio of 1.1, means that my inverter about 11% smaller in power. So it's okay. I have only one inverter. Then here is the tilt angle. So I tilt at the latitude here. Here is the ground coverage ratio. You can use 0.4. This is for the self-shading, right? So this parameter is linked to the self-shading, which means the minimum distance between the two arrays. I have two subarrays to avoid that there is shade from one to another. Yeah, so this can probably be 0.3, 0.4, depends. You can use 0.4. In fact, here there is the shading part. Yeah, also here you need to set up that. Aspect ratio is 1.5 is fine, doesn't matter. Yeah, so here it calculates the row spacing, okay, automatically. So basically by changing this parameter, it calculates different row spacing. I mean, I explained in my slides what does it mean, right? Price is very simple, and actually we need to do immediately soon. I don't know if we have time. So, but yeah. So basically, this relates to the theory. Let's see. For the shading is this one, right? So if you have let's say two array, right, or photovoltaics, you need to put the second row far enough from the first one, otherwise there is a shade from the certain, during maybe, in the winter, right, so which is the longest, right. So then, so here there is an explanation how to do reduce the self-shading. So how to calculate the distance to avoid self-shading. So roughly does the same thing, but he used a different way of using, this parameter, which is called ground cover ratio. Means, obviously if the ground cover ratio is very high, means they're very close to each other. Okay. Because it's a number between 0 to 1. So if it's 1, it means they're really attached here, which is not good. So if it's more, it means they're far apart. And you can see from what sound does, but it's the same. So but basically what I did here, I just calculated the row spacing of 4.2 meter for my case, and then I set up that ground ratio coverage, about to be given the same number instead. So it's you see 4.375 and I calculate 4.2 meter. I'm happy enough because you know if I change this, let's put 0.5. You see they come closer, okay? So that's too close probably, and what I use 0.4, maybe 2, I don't know. Okay. Yeah, 4.2. Okay, so that was just adjusting that one, adjust the separation between the rows. Okay, losses, you can leave the one I put here because the losses I have to know. So I put some standard losses. They can be slightly increased if you want. But, battery, okay. So there's a little bit of setting here, but again, in my battery is a desired bank capacity is a 30.6 kilowatt hour. Okay, where does it come from? Okay. 30.6. So the energy to battery. Okay, maybe bigger now. Okay. So the battery energy capacity in kilowatt hour should be the product between the battery ampere hour and the VDC. Okay, I don't know why I wrote here 11.5, maybe this file is not up to date, but energy to battery, so the battery here is battery ampere hour is 79.4 multiplied by VDC is 370. Whatever it is, the number is the kilowatt hour.
VDC 385.
13.6. I don't know why I have 11 point. Yeah, maybe. You see, battery ampere hour is 29.8. It should be the same number here. Battery ampere hour 29. 179.4. Okay. Should be 29. So it should be 30.6 in this example here, so 29.8. But anyway, here you can see the formula to calculate the ampere hour and the battery capacity and the ampere hour multiplied by VDC. So I'm not sure why it's not matching. So anyway, I calculated for this example that my battery should be 30.6 kilowatt hour. Just a bit. Here it says 29. Sorry, I don't know why it says 29. It should be the same. Okay. 29.6. It should be the same formula that I did there. So But anyway, this seems to be right. Okay, let me just check. VDC 1000. Discharge. So 79.4 multiplied by 370, how much is it?
29.378 2973 2935.
Okay. Oh, these are actually calculated here. Oh, okay. Okay, so I mean maybe this file here and the other PowerPoint are not exactly the same number. I might have used something different. So to calculate the battery energy capacity, you multiply the VDC times the energy battery per hour. Okay, which in this I don't know why I have 82.5 here and the other was 79. But anyway, it should be around the 30 kilowatt hour, 30.5, maybe a little bit less, right? So this number is the one that goes in here. You see here, desired bank capacity. So you basically determine the battery ampere hour, and then you multiply for the voltage, and you have the power. So, and this one, so the energy kilowatt hour, because you can also in hour. You can also do in hour. So for instance, say that you want 7 hours, but I did in kilowatt hour. And here the power of the battery can be also higher. This is the minimum that you can have, right, for this battery. You can also set the battery power of the equivalent to the power of the system. But anyway, I think to set it a bit smaller is fine. So the battery is connected DC, okay, because the scheme of the system is DC coupled. So you have the solar array, the charge controller, and then here there's the inverter. So the inverter is connected to the DC part of it. So basically sized, that's why it's sized on the system. So there are other connection that you can do. So this one example. I'm going to follow this. There is the desired bank voltage, okay, 370, send nominal voltage 12 and 2. So this one depends, these two here depends on the battery. Here I choose a lead acid battery, but for instance you could change the battery. So if you change the battery, this stays the same, but here I force you to change the value, default value. But here it's still 370, okay, because this has to be 370, the VDC. But this is more, I don't know, these are default value for specific battery. By the way, I go back to mine to use one. So this 370. And then the rest is, okay, DC connected, This value again, so no, their default value, you can leave the one I put. This also there's nothing to do. Battery life, nothing to do. This one, you can choose if you're different, but it doesn't matter. This, no, we don't do that. We don't leave it there as it is. Some parts they don't need to be because there's a lot of stuff that you can change here. Battery dispatch. Here we use as a dispatch peaks shaving. And also your minimum state of charge is 60% because I think I use them to discharge of 0.3, so it actually should be 70%. 60 or, I mean, I think it shouldn't be 70 here. Maximum stage of 35%. This is depending a little bit on what is your depth of discharge putting. Also this one day look ahead, perfect look ahead, that's okay. So there are different ways to dispatch this battery, you know, how you use it. This is the more common. And then there's nothing else. So basically you can follow the instruction here how to set SAM, except that for certain things you need to adjust for your specific project, okay? So I kind of put also there everything. You have this PowerPoint, right? So there is it here. What else? This is the system design. And this is the shading part, which that's okay. So once you do the simulation, okay. Basically, once you finish everything, you just simulate. That's it. Takes not much. Not too much. And then we can do this calculation manually, but it takes a bit of time. I mean, you can do a simple calculation. It's possible to do with Excel file, but here really is doing it hour by hour. That's the data guys every hour, so you can do monthly value easily. Yeah, so at the end it spits out the annual energy production and the capacity factor. So these two values are good. Because I checked the calculation and with a simple model, and that's all right. What else you get here? Levelized cost of electricity is not very correct. So that one I probably would calculate manually. I mean, with your, as I told you to do it. I don't know why, but it gets value much lower than what it should be. Also, simple payback period I think is okay, but the economics, you don't trust this, okay? Not too much. So what we can trust is this. Okay, so this shows you the monthly load compared to what it produces. And you can see that because we said, okay, we can, maybe not very much. Maybe I'll change something here. Because, okay, but anyway, in general, I produce more than the energy demand, okay? It seems strange though, because maybe this version is different. Anyway, what you should see here that the blue line are higher than the gray one. And so that's what you want to show as a result. This graph, no, it's actually the same that I got here, so higher. Sometimes I see something weird. Just late. Okay. Okay. So and you can make your table and your capacity factor. So very simple. So this what is this? The annual profile. This one is time series. Where is I get this one? Profile, okay. So here you have a profile of the production each month. But maybe because to show everything is hard, just look at the annual value, okay? And you can look at here what I'm showing. So it's called lifetime hourly data. So it's electricity to battery from system. So it's under this section here. So you see that you go on the profile and here electricity from system to load. Electricity, okay, you can also do load here. Is this load? I'm not big. Then what is I'm going to show here? Electricity to battery from system. No, sorry, because we need to look on the top here. Sorry, this is tricky. In fact, that's why I put this stuff, lifetime hourly data. Otherwise, they don't find it. So are on top there. And here there's quite a lot of things to look at. Okay, electricity to battery from system. Okay, so it's the PV that is charging the battery, and you see that it's charging then in the morning up to 12. Electricity to battery from system DC or AC are same, doesn't matter. Okay, electricity to grid from battery. So we don't sell electricity from battery to grid here, right? We haven't chosen to do that. Electricity to grid from system, yeah. So this is what we're selling to the grid. Electricity to load from battery, okay, so that's where the battery discharges to the load. Electricity to load from grid. Yeah, so we still need some grid because there is no sun, right? And battery is not enough, right? So we still need electricity grid. And then electricity to load from system. Here we go. So very clear, right? So the system is the PV. So you see that PV gives the load the power during the peak day. Then you need to use the battery after the sun is off, and then also some grid. Okay. Because it's not enough. Even though it is a very big size, we still need the grid. Because unfortunately you need the power when there's no sun. That's what the time profile is. When you turn on the electricity, sometimes the sun is already off because it's evening or it's morning, early morning. And it just produces most of the time during the day. The people don't understand this, but it is a fact, and this is very clear, right? So you can show this result in your report, and this is what I show here. You can also download this information if you want and plot it as you please. So this is another. This information is useful for the economics because, alright, so here to get this we go time series, hourly data, then we take our hourly data, okay, and here, see that's hard, I keep going, okay. Okay, so here our data, electricity from grid, so, okay, electricity from grid. I don't want anything else. Electricity from grid, electricity from system to load. Okay. Electricity load, electricity. I need three things. I need electricity from grid, electricity from system to load, and I need electricity to grid. Electricity to grid, okay. So it's a bit annoying because right, so that's what you need to have, alright? So at the end of the story, when you do your economics, that's what you need. You need to know how much you need from grid, how much you produce, and and how much you send to the grid, right? Send to the grid, take from the grid, send to the load. So because that changed the cost. So then you download this data as usual, right? If you download, you will have exactly the same title, and then you can calculate the total of that, right? So total system load. Okay. So here I want to know how much electricity I need from the grid in 1 year. So for this system, I need 16,409 kilowatt hour from the grid. How much electricity I sell to the grid? 4,791. And this is the total produced, 20,345. And this is total electricity that the system sent to the load, 3,936. Okay. So this one is simply by downloading the data and sum up them, because you have hour by hour, right? So this one comes up that I need to supply 8,727 to my load. Alright, so then from here I can calculate how much money I get from the grid. So you're gonna sell a certain price to the grid, and then what you produce is saving, right? And generally when you sell to the grid, you sell much less than what you buy. So in other words, if your buying is 40 cents per kilowatt hour, I'm just saying, right? And you sell probably at 10. But when you're saving money, like you don't buy it, it's like 40 cents per kilowatt hour. So you can do your economics, you know, in this way, and see what is, what you're getting out of this system. So the economics. So obviously you could set up the economic with SAM. Economics with SAM, it can be done, but as I said, it's not. I don't like what it does, and so you can set up. You have to economics. You need to calculate the capital cost. Cost for the photovoltaics. Find out what is the typical. It's relatively. It's about $1 per watt now. Only the photovoltaics. Then you have to pay for the inverter, right? And the battery. So the battery is the most expensive one. So the battery can be minimum $1,000 per kilowatt hour, right? And then it can be slightly less if you have a lead acid battery, but it can be more if you use a lithium-ion battery. So this number that I put here, I don't know if I make this sense, right? Probably $2.6 per kilowatt hour per watt. How much is the system? Yeah, at the end what you look at is what is the dollar per watt. Let's say that here the battery, I think I underestimated the cost. In fact, So the battery is much more than this, right? So the battery probably 800. Because I'm using a poor battery, like that, so like the one on the car, basically. Maybe a used one. Yeah. And so if I do this, you see the price goes up. Actually, it did. Sometimes it doesn't do the calculation, really. 62,000. Probably it's okay with what I said here. So. Okay, so yes, now it's fine. So I'm getting about 4.6. So as soon as you have the battery, then the cost of the system per baht goes up. Also here you can set up operating cost like you know, annual cost $20 probably below, but maybe $100 per year. This maintenance cost. There is a place where you can put the financial parameters. Okay, 20 years project, and here the real discount rate. Okay, the discount rate here. I think I put 8%. You can have the salvage here. So I actually set up the economics, apart from underestimating the value of the battery, the cost of the battery. But when you do the simulation with SAM, you get very positive results. I mean, in terms of levelized cost of electricity, it was given 11 cents per kilowatt hour. I'm expecting a 20 up to 30 cents per with the battery. So it depends on the system, right? So, but probably the 20 cents per kilowatt hour. So, and it's very unlikely that you get a positive present worth. But you can try, you know, so see what happens, right? But anyway, everything for STEM is pretty much just few things you need to fix. If you have problems, just email me, right? When I was back to Melbourne, you can send me an email. I can't understand how to do that or something, you know. No problem. I really like this project, so I'm happy to have. It's not just a simple example like the one that we're doing. I mean, those are okay to understand, but this is really more, you know, professional approach. But of course, in order to be able to understand SAM, you have to do all the basic, you know, because otherwise, what is this nominal? What is this open circuit voltage? What is this VDC? You know, you don't understand until you do the basics. So it's also a way to show you actually what you're studying is really important, because that's what people use, you know, in the real world. So, and that's it. So you have all the description here. So once you have your watt hour or kilowatt hour, right? So then you can convert that in dollar and do your economics. You know, find out the cost. But yeah, electricity costs are, yeah. I mean, in Australia, I think depends on the state, but the buying cost of electricity is around 30 to 40 cents per kilowatt hour. And the selling to grid is between 10 and 12, 15. They're gonna reduce more. I don't know in Singapore, right? So you could use the rate of Singapore if you want, but sizing in Australia, if that's more easy for you, you know, to get the value right. So. But we use the dollar as, you know, that unit. Strange. We change slightly between a country to another, but it seems pretty much, you know, making sense. You know, the dollar, whatever it is, as a reference. That's all. Okay, for this. I hope I didn't scare you up with this project, but yeah, my students in Australia, I think now they like it. After I forced them, you know, like they like it. But yeah, it was smooth this year, very smooth. Okay, what we have left to do is a little bit or more analysis, solar thermal collector, and a few examples of the solar thermal collector. They are quite easy. Did you already cover this topic, solar thermal collector, or not?
No.
Probably not. Okay, we just